Hello everyone and good evening to all of you. Now, before we start, tell me in the comments, am I audible? Is the voice clear? Am I visible? Is the audio quality good? I'm waiting for your comments. Is everything fine? Is audio good? Is video good? Give me a thumbs up in the comments before we start. Okay. Thank you, Myra. Thank you. Malar Vidhi. Clear. Thank you. Thank you everyone for giving the confirmation. Good evening, Malhar Vizi. Good evening. Okay. So let us start today's class. Up until now, we are done with the two very important theories of the continental drift and convection currents. These two theories have led us to another very important theory of sea floor spreading. In today's class, we will be dealing with sea floor spreading and plate tectonics. Plate tectonics is a very important theory as far as geomorphology is concerned. Good evening, Myra. It's very important theory, the plate tectonics. Now, before we start the seafloor spreading, let us get into the background of why this theory came into being. Initially, what was thought that the floor of the ocean or the bottom of the ocean is flat. There are no relief features. But with the passing of time, with the improvement in technology, hello Navdeep sir, good evening. So with the passing of technology, it was figured that the bottom of the ocean is not the way it was thought to be, but there are many relief features present in the bottom of the ocean, like the guyors and the seamounts, the mid-oceanic ridges and trenches, and so on and so forth. So this led to the increased interest to find about the bottom of the ocean. So many scientists and the geologists tried to figure out what exactly is going in the bottom of the ocean. Okay, clear? That is why some of the scientists led to increased interest to find about what is going in the bottom of the ocean, and eventually a very important theory came into being given by Harry Hess. That is the sea floor spreading. What is a sea floor spreading? As the name suggests, sea floor spreading, that means something is spreading. That is exactly what is given in the theory. This theory tells that their sea floor is like a conveyor belt. What is a conveyor belt? Hania Mir, hello, 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 hi. What is a conveyor belt? That is it is continuously being formed and destroyed. That means the oceanic crust is continuously being formed, the new crust is being formed, and eventually it's being destroyed. At one place, if it is formed, at the other place it will be destroyed. So to understand this theory, I'll be drawing a diagram here so that you are able to understand the theory better. Okay? So you can just follow the diagram, and you can also draw it if you're taking down the notes, because it's very important to be good at diagrams. My diagram will not be good, but I hope you will draw a good diagram so that you can get good marks in the exam. So see, this is the ocean floor. Just a second, I'll be drawing it with white so that it's visible. If there is any problems with the visibility of the color, if the color is not visible, you can tell me in the comments. Okay, so this is the ocean floor that I'm drawing. It is the oceanic crust and the slab. Now see, what this theory exactly tells us is what is going to be explained with the help of the diagram. This is the bottom of the ocean that I have drawn here. Now this is the lithospheric slab. This is the continental part. Clear? This is the continental part here, and again, now tell me one thing, when we studied about the interior of the earth, what did we study? What lies beneath the lithosphere? As you know, lithosphere includes the crust and the uppermost part of the mantle. Then what followed the lithosphere? What was after the lithosphere? It was asthenosphere. And what is the property of the asthenosphere? What is asthenosphere composed of? Asthenosphere is composed of the magma or the semi-solid material. So that magma, due to the convection currents, that is how you have to connect the linkages. Because of the convection currents, the magma is continuously in motion, as you already studied in the sea floor spreading. Okay, sorry, in the convection currents. Now, the magma is continuously in motion. It will be going up at some places, like I'm showing with the arrows. Just look at the arrows properly. It will be going up at some places and it will go down at other places due to the convection currents. This is how the convection currents work. Okay. Now, what you will figure out in this diagram is that if the convection currents is the ascending limb, then there will be a descending limb as well. Now, seafloor spreading concept tells us that wherever there is an ascending limb, well, not everywhere, but at most of the places, you will find the crustal thinning and eventually there will be the formation of rift. If you look at this image here that is drawn with the yellow, there is a rift present here. The plates are separated because of the rift, because the magma is going up. So it is going to create a rift that I have already discussed in the previous class. If you have not seen the previous class, you can see it once how the rift is formed. Once there is rifting, there is a crack. What is a rift? There is a crack. Then the magma will come out of the rift. See, the magma will start to come out of the rift and it will start to get solidified. Once it comes out of the rift, what will happen? It will cool down and start to get solidified. So it will come out and start to get solidified on both the sides of the rift. It's not going to be on the only one side of the rift. Is it clear? It will be on the both sides of the rift. See this yellow, the red color one that I'm showing here with, see, if you're not visible, the pink color shows the solidified magma. Once it comes out of the rift, it will solidify at these places and it will continue. Now, look at this image very carefully. What's happening inside of the earth is this. These are the convection currents that are continuously moving like this. When they move, they will make the lithospheric plates to move as well. Because of the magma coming out continuously, it will go on like this. New magma will come to this place, the older one will go here, the new magma will come here, and the older one will follow. So it's very important to know that continuously near the ridge or the rift, the new crust will be formed. And what is going to happen to the already formed crust? It will continue to move outside, away from the rift. Like the example, the continuous forming of the crust near the mid-oceanic ridge, and the older crust is going to move away from his. This is the older crust, and this one is the newly formed crust. Is it clear? Is it clear that how the crust is formed and anything else? If you have any confusion, you can ask me. The new crust will be here only and the older one will be moving towards the other end. Then eventually when it will reach here, once it reaches this place, what is going to happen? You see, there is a conversion with the another. In the interior of the earth, there is another like this convection current going on. This is the descending branch. Again, the two converging branches from one side and other. Then there's continental crust as well. This will lead to the subduction of this. As you see, this is a bit curved, right? It is curved because it's going to subside. It's going to subduct. It's going to subduct under the continental crust. This is the continental crust. See, this is the continental crust and this is the oceanic crust. Is it understood how it is formed at the rift and how it moves and then subducts under the continental crust? Clear? Okay, thank you. Why is it subducting? Why is the crust subducting under the oceanic crust? This is a question for you guys. You tell me quickly. I'll explain it. Why is it subducting? But tell me quickly in the comments, what is the oceanic crust composed of? What are the main components of the oceanic crust? I'll give you an example. Because the oceanic crust is denser as compared to the continental crust. This is a hint for you guys to answer. What is the oceanic crust composed of? You answer me in the comments quickly so that I get an idea that you are revising the previous classes. Otherwise, you will not be able to get it. Why is it subducting? There has to be some reason now. Why is not this plate subducting? Why is not the continental crust subducting? What is the main reason that this plate, when it moves to this place, why is it subducting? There is a reason, there is a specific reason. As I told you when we were studying the interior of the earth, Cause it's heavier, composed of silicon and magnesium. Zainab, correct. That's a great answer. That means you are revising continuously. You're right. Because it's made up of silicon and magnesium, it is heavier and denser as compared to the continental crust, which is made up of silicon and aluminium, Cl and Cma. This is the composition of the continental crust and the oceanic crust. Because the oceanic crust is more denser, that is why when it reaches here, when it collides, when it gets in contact with this, it starts to subduct and it goes in the asthenosphere. This is asthenosphere. When it goes into the asthenosphere, what is going to happen? Because of the high temperature in the asthenosphere, it will melt. Seema, Hania, Mir, correct. That's right. Because of the high temperature, this will start to melt. When it will melt, again the convection current, it will go into the asthenosphere, then it will melt again, this will continue. The process will continue. So this process, what do you understand from this process? It is like a conveyor belt. What is a conveyor belt? When you go to the airports and all, you know how you put your bags on a belt, then it goes and takes your bag. That is exactly what is happening here. Near the rift, the new crust is formed, and when it comes to this place, the subduction place, the old crust is present. Now I want to ask you a question. If there is a question in the exam, then where will you find the newest possible crust and where will you find the oldest crust in the ocean bottom? So the answer is very simple. The newly formed crust will be near the rift and the oldest crust will be near the subduction zone. Clear? This is the concept of sea floor spreading, and this should answer your confusion if you have the confusion that was there by asked by some questions some students last time, that sir, if a new crust is continuously formed, then why is the earth not expanding? Obviously it's very common sense. If the crust is continuously being formed, then earth has to expand, but it's not expanding because near the ridge is newest, right Zainab? That's right. And when the new crust is formed, you know, it is subducting at the same time, so it's not expanding. That is the reason why the crust, the oceanic crust or the earth, is not expanding. It's clear about the continental crust. Okay, this is all about the sea floor spreading. Now some important things that you need to know about here is that, look at this diagram. This is a diagram of the bottom of the sea floor. Just a bit of confusion for some guys. If there is, I'm going to clear it here. This red line, if it is visible here, this red line is called the rift. It is the rift. It is not the ridge, but a rift, the crack. So the crack is a rift. Don't get confused between the two. The crack is a rift, and the raised part, the blue color part here, the raised part is a ridge. So don't get confused between the rift and the ridge. So the raised part is a ridge. So don't get confused between the two, what is a rift and what is a ridge. Okay, this place is called the mid-oceanic ridge. Clear with the mid-oceanic ridge? What is a mid-oceanic ridge? It's the place where there is continuous rise of magma and formation of peaks like the mountain, small peaks. This leads to formation of mid-oceanic ridge. It has a rift in between from where the magma comes out. And very important, the newest crust is near the ridge and the oldest one is near the subduction zone. This is about the sea floor spreading. Now the question, are there any evidences? Do we have any evidences regarding the sea floor spreading? Yes. First is the age of the rocks. As I already told you about the age of the rocks. See, I'm going to draw a diagram here. This is again the lithospheric slab or the ocean base on two sides. Now, what was observed while doing the carbon dating about the rocks that are present in the ocean bottom? What was observed that they figured out that the rocks that were present near the rift, say here, were younger on the both sides. The rocks present on the both sides of the rift had the same age from the same distance. Say if they have taken the measurement of say 1 or 10 or 100 meters to the either sides of the rift or the ridge, the rocks were of the same age. Say these rocks, this is just an example, this is not for fact. These rocks, say for example, they were 1000 years old. This is not the case. The rocks are millions of years old. This is just for the ease of understanding that these rocks were 1000 years old. When they moved away from this, the rocks that were present here on either side of the rift, these rocks were only 500 years old. These rocks were 1500 years old. Okay, so these rocks were 1000 years old, but when you move away from it, these rocks were 1500 years old. And when they moved further away, say here, the rocks were about 2000 years old. So again, the same thing, when they moved away from the carbon dating, yes, that's right, correct, carbon dating. So when they moved away from the rift, they started to observe that one thing, that the rocks on the both sides, on the either sides of the rift, were of same age. That is, the rocks equidistant from this were of the same age. And one more thing, as they moved away from it, the age of the rocks started to increase. This indicates that as the magma is coming out from here, it solidifies here and forms the new crust, but then again the magma is coming continuously and the plates are being pushed. That results in the movement. This will move towards this direction, and eventually the age of the rocks increased as they moved away from this. Are you able to figure it out, how the age of the rocks increases as we move away from the rift or the ridge? Because of the newly coming magma and the movement of these plates, because the convection currents under the earth are moving like this, right? They are moving like this. This results in the movement of these things, and that is why the older rocks are moving towards the other side. That is number one point. This is the first evidence that the rocks on either side of the rift were of same age, and the newest formed rocks were near the ridge as compared to moving towards the subduction zone. Number one. Number two, what they observed was that the oceanic rocks or the oceanic floor, the rocks that were formed in the ocean or the oceanic crust, was of a maximum of 300 million years old. So these rocks were no more than 300 million years old. So that means they are not that old as compared to the continental crust. That is somewhere found to be more than 3 billion years old. Can you imagine the continental crust being 3 billion years old and the oceanic crust being 300 million years old? There is a huge gap between the two. That means the continental crust once formed is like that, but the oceanic crust is continuously being formed. Okay? If you have any confusion, any doubt of how the age of the rocks have helped us to predict the seafloor spreading, you can ask me in the comments. Till then, just take a look at this data, how there is a huge difference between the two. New rocks, old rocks, the continental rocks way too much old as compared to the oceanic rocks. If you want an example for this, this is an example of the Atlantic Ocean. Atlantic Ocean that lies between the American continents and the Europe and Africa. See, in this diagram, it's clearly visible that, see this red area that is here. If you look at this red area, this is near the ridge. Ridge is this one, the black one that's passing here. The center one is the ridge. The red area is of 20 million years. It's formed 20 million years ago. This is an actual image of the Atlantic bottom. This is an actual image formed 20 million years ago. So the bottom of the Atlantic Ocean is 20 million years ago. Okay, Zainab. And then when you move away from it, then go to the green color area. It is 120 million years old. So as you move away from the rift, it is clearly visible that the age of the rocks is increasing as well. And it is same on both the sides. If it is 120 million years, you can see it on the either side of the rift that it is same. Equidistant rocks are having the same age on either sides of the rift. And then go away from it, you will find 180 million years ago, this blue region that is there. Is it clear how the age of the rocks have helped us to calculate or understand the sea floor spreading? This is the theory that the age of the rocks on the ocean floor increases with distance from the mid-oceanic ridge. That is what I told you already. As you move away from the ridge, the age of the rocks is going to increase. The oceanic crust is much younger as compared to the continental crust, as the example was given that it's no more than 300 million years ago as compared to the continental that is at places 300 billion years old. Is it clear how the age of the rocks have helped us to understand the seafloor spreading? So let's move to the next evidence. What is the next evidence? It is the magnetism. It's related to magnet. But before we go to the magnetism, we have to understand that Earth has a magnetic field of its own. If you don't know about it, then Earth has a magnetic field of its own. If you look at this image, you will find that there is a proper polarity. You will find a south pole and a north pole of the magnet. Because of this, the magnetic field of the Earth is created. Now, how does the Earth have its magnetic field? What do you think? Now, if you go back to the interior of the Earth, then just go back and find that the interior, the core of the Earth is solid, inner core. Go back to the interior of the Earth and you will find out the inner core is solid in shape. Okay. Then what is the outer core? It is liquid. The outer core is in liquid shape. This is the outer core and it is liquid. Now, how does a magnet work? If there is if you have gone through the physics, you know how a coil is turned around an iron bar and it leads to the formation of magnetic effect. Is that clear? That is how the magnetic effect is created in the Earth as well. Because of the continuous convectional currents going on here, there is a specific direction in which the convectional currents will be there. Because this is liquid, because of a lot of activities in this region, the outer core, and it is wound around the solid core, it will lead to the formation of magnetic effect of the Earth. This is the magnetic field of the Earth. Because of these activities, see, because of these kinds of activities, there is a formation of a magnetic field of the Earth. This is how the magnetic field of the Earth works, with a proper polarity as well. Now, another factor is the paleomagnetism. What is a paleomagnetism? It is studying about the ancient magnetic effects that are there. Now, look at the diagram. This is a very important concept that you have to look because it's very tricky, so you need to understand it properly. If you have any confusion regarding while I'm teaching it, you can ask me in the comments if I am missing something. If you're not able to understand, just tell me in the comments so that I'll stop there and tell you, because it's going to be a bit tricky, so just focus on this. Now, let us assume that this is Earth. Okay, this is the north pole of the magnetic Earth and this is the south pole. Just assume this as such, or take north in the bottom and south there. If this is for the ease of understanding, so that you don't get confused between the north and the south. This is the magnetic field of the Earth. Clear? Okay. Now, what is going to happen is Earth will have its own magnetic field like this. Earth will have its own magnetic field. Now imagine, let's go back to the sea floor spreading case. Here, what is going to happen there is when the molten lava is coming out of the Earth, it is not solidified. It is first in the liquid form. Because it will contain some of the iron or the ferrous elements, you know, the elements that get attracted to the magnet. So it will align. Because the magma, when it will start to come to the surface, it will be in the molten form. Now imagine the lava that has come here. It is in the molten form. It is not yet solidified. This yellow color is not yet solidified. It is molten. Okay. It's still molten, not solidified. Now what is going to happen? Because it contains the ferrous elements, the elements that are affected by the magnetic field of the Earth, it will align according to the magnetic field of the Earth. Say it will start to align, all the elements in it will align like this. They will all align in the same direction. Why? Because there is a proper feature of the magnet that the north pole will attract the south pole. So these elements, this is something that is going on in the Earth. Everything is going to align itself as per the field, whatever the field is. So everything will align like this. Okay, clear how these elements are aligning themselves? If you have any issues, you can tell me. Are you understanding how the elements are aligning themselves as per the magnetic field of the Earth? Now, go back to the past and imagine the convectional currents that I showed you here. The convectional currents that are taking place in the outer part of the core, the outer core. They can easily get reversed because it's all about radioactive stuff and other things that lead to the direction. Now imagine due to the convection currents, these currents change their direction. Now look at this is the red one. This is already done. Now after some time, if the convection currents change their direction, they start to go like this. What is going to happen if the direction of the convection currents changes? Then the magnetism, the polarity of the Earth's magnet is also going to change. It will also change. If the direction of the current is changed, you can do it in the physics. If you change the direction of the current in the coil that is wrapped around the iron bar, you will figure that the magnetism will also change. The feature will change. Whatever was north up until now will go to south. But before we go to that, this is now solidified, because once they have set, after that it will solidify. Now after say 10 million years, once it's done, the polarity of the Earth is changed. Okay. So whatever was north up until now will be south, and this end will be north. Now what is going to happen if the polarity of the Earth is changed? The lava is continuously coming out of the Earth. That is for sure. The lava is continuously coming out from the mid-oceanic ridge. What was found that the magma that came out had different polarity. This polarity was when north was here and south was here. Now, because of the change in the polarity of the magnetic field of the Earth, the elements that are present, or the ferrous elements present in the molten lava, this is now solidified. Keep it aside. This is how it is. The elements are going to be like this, because once the element is solidified, it won't change. The polarity will not change after that, because it's solidified. When it was molten, these particles had the freedom to move. So they aligned according to the magnetic field that was present at that time. After that, once the polarity is changed, you will figure out that the elements will align like this. It is all dependent upon the polarity of the magnetic polarity of the Earth. What is the direction of the magnetic polarity of Earth? When the direction was reversed, the elements aligned like this. Now, because the south went to the top and north is here, the elements aligned like this. After that, it will solidify again, and once it will solidify, they will remain as such. Is it clear how the polarity is working? We have to connect it to the seafloor spreading as well. So if it is clear up until now, you can tell me in the comments, so that we can connect it to the seafloor spreading as well. If this is clear, how these things are aligning, then it's easy to compute the seafloor spreading case again. See, if this is the seafloor again, when the molten lava was coming out of the Earth, Myra, Vani, yes sir, thank you for the clarification. When it will come out, say for example, if the direction was like this, the polarity will be like this first of all. So it's going to be like this. This is the first material. You will find this polarity. Clear? This is how the elements will be like in the first instance. After that, suppose after a few million years, once the Earth will change its polarity. When the polarity of the Earth will change, the other features will have polarity like this. It will not be the same. So the magnetic polarity is very important to understand the seafloor spreading. That is what was figured. Alternate patterns of reverse polarity and the magnetic and reverse polarity has helped us to understand the seafloor spreading. It was again found that the rocks equidistant from the ridge were having the same polarity. So this and this will have the same polarity, and this will have the same polarity, because of the condition of the magnetic field of the Earth at that time. Is it clear that how it works? This is a diagram to help you understand better. See, this is the ridge. This is the ridge from where the lava is coming. You see, these two are equidistant. You will see the direction is this. Then this and this one is again, you see the direction of the arrows is same. That means the magnetic direction is same. The rock created at this time will have the same polarity. Malar Vizi, very clear sir. Thank you. Hania Mir, clear. Thank you. Thanks for the thumbs up everybody. So this is how the polarity gets affected because of the movement of the Earth. Nice way of explaining. Thank you very much. Now, this is what I was telling you up until now. Use of magnetometer to check the polarity. They use the magnetometer to check the polarity. The study of paleomagnetism. What is paleomagnetism? To study the magnetic effects in the past. That have helped us to understand the sea floor spreading. So this is all about the evidences that we have regarding the sea floor spreading. So this is a brief summary of sea floor spreading. You can see at this point the magma is coming out and the rocks are moving like this. The newest one will be here and the oldest one will be here somewhere, going towards the subduction zone. Is it clear how the things are working? This is a summary for you guys. If you have any confusion, you can ask me. So this is the age of the seafloor is progressively older away from the mid-oceanic ridges. As I told you, this is a very important thing that you need to write down the age of the rocks where it will be oldest. It can be a very straightforward question that can be asked. Where will be the oldest rock in the seafloor? It will be far away from the ridge, and the elevation of seafloor is progressively lower. This I missed, so take it down. The rock will be highest near the ridge, and then as you move away from it, the slope will be less as compared. The rocks will not be that high as compared to near the ridges. Is it clear? So is everything clear about the seafloor spreading? So up until now we are done with seafloor spreading, we are done with the continental drift, and we are done with the convection currents. Now comes the grand theory of plate tectonics. What is plate tectonic theory? What is it? Earth's surface is made up of several tectonic plates. These plates move and interact with each other, causing earthquakes, volcanoes. This is the basis of plate tectonic theory, that the Earth's surface is made up of many tectonic plates. And because of the interaction of these plates, there are various physical features like earthquakes, volcanoes, mountain building, and many other things. Then there are multiple types of mountains and other things like the fold mountains, the block mountains. So we'll go step by step. Is it clear what the tectonic plates theory states? It states that if you look at this diagram, these margins that are drawn by the black area, these mark the plate boundaries. That is, the Earth is made up of multiple plates. Now, first question I want to ask you is, what is a plate? You might get confused. Okay, Earth is made up of multiple plates, but what is a plate? What is a plate in the first place? What do you think the plate is? See, if you go back to the interior of the Earth, when we studied about the interior of the Earth, this was the first layer called the crust. After that we had mantle. This was the mantle, but the uppermost part of the mantle, say this much. The crust and the uppermost part of the mantle was called the lithosphere. These were solid layers that were present there, and this is what a plate actually is, the lithospheric slabs. These are the plates. So Earth is made up of these plates, the lithospheric plates. If you look at these are the lithospheric plates. And why are these responsible for all the features that are there on the Earth? Because lithospheric plates lie on the molten asthenosphere. Again, the interior of the Earth concept, where the lithospheric plates float. They move on the semi-solid asthenosphere, and that results in various physical features on the Earth. This diagram shows that the Earth is made up of multiple physical features, multiple plates, and the plates are normally divided into two types, the major plates and the asthenosphere plus crust. Yes, Zainab, that's right. Because of that, you will see that these regions will have two kinds of plates. Earth is made up of two kinds of plates. First one, hi, hello. Because of this thing, some plates are called the major plates and some plates are the minor plates. That we will study later, which one is the major plate and which one is the minor plate. Now, because of the interaction of these plates, all the important physical features like the mountains and other places are formed on the Earth. If we look at the interaction of these plates, suppose this is plate 1, this is plate 2, clear? This is plate 3, and then we have plate 4. These are 4 plates. Now, depending upon the movement in the asthenosphere, how the continental, how the asthenosphere currents, they will determine what is going to happen with the plates. Say for example, if we take the movement of the convectional currents like this, if this is how the convectional currents are moving like this, then what is going to happen with these P1 and P2? They will be coming towards each other. They will start to converge because the convection currents is driving them towards each other. They are coming towards each other. Look at the direction of the arrows, like this and this. Clear? They are getting driven towards each other. So this will lead to convergence. Likewise, let us look at plate 3 and plate 4. If the current is going on in this direction, then what is going to happen? The plates will start to move away from each other. The plates will move away from each other, and this is called the divergence. So these are the two movements associated with the plates on the earth, the convergence and the divergence. So the plates will start to converge when there's a current going on like this, and the plates will start to diverge when the convectional currents are going like this. These are the two directions associated with the movement of the plates. Then there is one more direction that is associated with it, is the transform boundaries, where the plates will neither come towards each other nor go away from each other, but will go past each other. When they will go past each other, then this will lead to the transform boundaries. So basically we have three types of boundaries associated with the plate movement. This is the first type, that is the divergent plate boundary. Clear? This is the first type of movement. This is the second type, where the plates will come towards each other. And then we have third, look at the arrows, they will go past each other. Neither they will transform, they will not converge nor diverge. It will be called a transform plate boundary. Is everything clear? All good? So these three plate boundaries are also called constructive boundaries, destructive boundaries. Why is the divergent boundary called the constructive boundary? If you look at this boundary, you will find out that when they move away from each other, the magma from the bottom of the asthenosphere will start to come out of the earth, which will lead to the crust formation. That is why it's called the constructive boundary. And same thing goes with the convergent boundary. It's called destructive because when they will converge, one plate is going to subside under the other. That will lead to the destruction of the plate. So it is associated with the formation of the plate or the destruction of the crust. That is why the name constructive and the destructive. So this is about the boundaries. This was a brief introduction about the plate tectonics. I think we should limit our lecture to this much because we have done with the seafloor spreading, and plate tectonics is a very important lecture that we are going to deal with because it is the lecture that is going to help us understand various features, like we'll be understanding how the Himalayas are formed, how the Appalachians were formed, all the important, how the Rockies and the Andes, all these things. This is the theory that is going to help us understand all these things about these theories. If you have any questions, you can ask me in the comments. And if you are preparing for UPSC, then Unacademy's got a very beautiful offer for you for just 24,999, where you will get the best quality educators to learn from. And we have got 3 batches that have started in full English. If you want, there is a batch in Hindi or bilingual. You will get all the batches. We have batches in Hindi, English and bilingual and all the language. Whatever you want, that is present for you on Unacademy. And if you have any questions, how are you so fair, sir? I am not so fair. It's the lighting that has made the thing. It's not the case. Actually, it's the lighting. Because of the lighting, it looks like so. I'll look into the matter and get the lighting sorted. Clear, sir? Okay. So I think we don't have any questions. So are we done with this? So that is all about the seafloor spreading. In the next lecture, we'll go to the plate tectonics, and I hope you have understood everything. See you next time. Till then, goodbye.